A pristine marine aquarium looks effortless from the outside, but open the cabinet doors below the display and you find the mechanical engine that actually keeps the ecosystem alive. That engine is called a sump. It is a custom-built secondary tank sitting below the display. It hides all your bulky life support equipment, increases the total water volume to dilute pollutants, and acts as the literal heart of your closed-loop circulation. Building your own requires strict adherence to fluid dynamics. Today, we'll calculate exact chamber dimensions, select biologically safe materials, and execute a flawless silicone installation. Mastering this construction process yields a highly specific result. Moving your hardware into a calibrated separate water volume stabilizes your temperature and salinity, providing the critical margin of error required to maintain sensitive marine life. This diagram outlines the industry standard for marine filtration. It takes a single open tank and divides the space into 3 distinct internal chambers. Chamber 1 is the drop zone. Raw, untreated water drains from the main display into this section. Here, mechanical filters capture solid debris, and a protein skimmer physically strips dissolved organic waste out of the water column. Next, the water flows over the first glass divider into Chamber 2, the processing zone. This is a biological refuge. Aquarists use this middle section to cultivate macroalgae that consume nitrates, or to house chemical media reactors. Finally, the water spills into Chamber 3, the return zone. This is the staging area where your main pump pushes the fully cleaned water back up to the main display. By forcing the water through this exact sequence, the system systematically strips out organic waste, stabilizes the water chemistry, and heavily oxygenates the liquid before it returns to your corals and fish. Translating that theory into physical glass requires strict calibration. Your first step is to ignore the product dimensions listed online for your equipment. Manufacturer specifications often differ from the actual physical footprint by crucial fractions of an inch. Instead, you must perform a dry run. Take your actual physical protein skimmer, media reactors, and return pump and place them directly into the empty, dry glass tank. Position them carefully. You must account for spatial tolerance. If you place a skimmer flush against a glass wall, you will not be able to fit your hands around the collection cup to remove it for weekly cleaning. Once the hardware is spaced correctly, take a permanent marker and draw physical lines directly on the glass floor to map out exactly where your dividers need to go. Skipping this physical calibration is the leading cause of DIY sump failures. Measuring around the real hardware ensures your expensive equipment actually fits into the chambers once the silicone permanently cures. With the layout marked, you need to acquire the dividers, also known as baffles. These must be made of glass, cut to a minimum thickness of 5 mm, with fully polished edges to prevent injury during maintenance. Avoid cheap alternatives. Thin picture frame glass will shatter under the water weight. Acrylic panels will warp over time and eventually tear away from the silicone, collapsing your entire filtration sequence. To bind the glass, your chemical selection is absolute. You must use 100% pure silicone. Do not buy standard bathroom silicone. Bathroom sealants contain antifungal and anti-mold chemical additives. If used in a sump, those chemicals will rapidly leach into the water column and poison the marine microfauna you are trying to cultivate. Choosing glass over acrylic prevents mechanical collapse, and pure silicone over bathroom sealants prevents chemical poisoning. Your structural materials are the first biological defense for the ecosystem. Moving to assembly, your first vertical glass pane must sit perfectly flush against the floor of the tank. This creates a solid wall that forces water to flow over the top, blocking any debris from moving across the bottom. This schematic illustrates the next critical feature, the bubble trap. Looking at the blue directional arrows in the internal chambers, you can see how water is forced over the first baffle and then driven downwards underneath a second suspended baffle. This forced downward flow pops microbubbles generated by the skimmer before they can reach the return pump. To build this trap, take 2 wooden blocks cut to exactly 1.5 inches and place them flat on the floor of the tank. Rest your second pane of glass squarely on top of them to suspend it perfectly in place while gluing. Secure the glass using a caulking gun. Apply consistent pressure to run a smooth, continuous bead of silicone down the entire vertical seam where the baffle meets the tank wall. Once the bead is laid, you will likely notice the glass pane is slightly crooked. You will feel an intense urge to push it and straighten it out. Do not touch it. Pulling or twisting a pane of glass after the silicone makes contact introduces tiny air pockets into the bead. Those hidden pockets destroy the watertight seal between chambers. In hydrodynamics, a misaligned, fully sealed joint functions exactly as designed. A perfectly straight but compromised joint allows water to bypass the filtration stages entirely, resulting in total system failure. Leave it alone. Step away from the tank. The silicone requires a strict 24 to 48 hour curing phase in a well-ventilated room before it can safely hold pressure or touch water. Once fully cured, activate the return pump. You will see the water cascade over your first flush divider and immediately sweep underneath the elevated pane of your newly constructed bubble trap. By locking the glass at a specific height, you guarantee the water level in the first chamber never fluctuates. Your protein skimmer now operates at maximum efficiency 24 hours a day, regardless of how much water evaporates from the system. Furthermore, that evaporation is now forced to physically manifest entirely in the final return chamber. This isolates the water loss to one small section, making your daily freshwater top-offs highly predictable and easily automated. By ignoring theoretical dimensions, carefully mapping your physical hardware, and executing a rigid 3-chamber design, you turn an empty glass box into a self-regulating hydrodynamic engine. Step away from the tank. The silicone requires a strict 24 to 48 hour curing phase in a well-ventilated room before it can safely hold pressure or touch water. Once fully cured, activate the return pump. You will see the water cascade over your first flush divider and immediately sweep underneath the elevated pane of your newly constructed bubble trap. By locking the glass at a specific height, you guarantee the water level in the first chamber never fluctuates. Your protein skimmer now operates at maximum efficiency 24 hours a day, regardless of how much water evaporates from the system. Furthermore, that evaporation is now forced to physically manifest entirely in the final return chamber. This isolates the water loss to one small section, making your daily freshwater top-offs highly predictable and easily automated. By ignoring theoretical dimensions, carefully mapping your physical hardware, and executing a rigid 3-chamber design, you turn an empty glass box into a self-regulating hydrodynamic engine.